Hi, my name is Sean Hawk. Welcome to my presentation on machine learning and um, Strava derived analytics for marathon prediction using GPS data. So the goals of my project were twofold. Number one, I wanted to be able to um, predict a marathon time for an athlete based on 3 months of their previous training runs up that they had uploaded to Strava. And number two, I wanted to determine which features of this data set were most positively correlated with a successful marathon time. For instance, what is more important, a faster training speed, um, longer training runs, or maybe the elevation delta is most important. I'd like to know. Let's find out. So Strava, if you're not familiar, it allows users to upload runs from their GPS watch, be it Garmin or Apple Watch or a Sunto, doesn't matter. They can upload all their training runs to a database which stores and collects all their training data. I downloaded my Strava data into R using the Strava API and a package called rStrava. And so after doing this, I found I had about 3,800 runs, and each run had 60 attributes, such as distance, time, average pace, elevation, how many feet of climb, average heart rate, etc. And of these about 3,800 runs, 119 of them were races. So after downloading the data from Strava into a data frame in R, I wanted to normalize the data. And to do this, I wanted to make a performance metric that would equate efforts of different races, of different race distances. For example, a good time for a 5 mile race might be very different from a good time in a 10 mile race. It's not just doubling the effort. It's because every time you increase the distance, the maximum speed that an athlete can run that race, it's going to drop off by a percentage. And Peter Riegel is an example of modeling this. He came out with the Riegel formula, and he says that the speed decreases by a good 7% every time you double the distance. So the method I used to normalize my data was using VDOT. And VDOT is a mathematical equivalent of VO2 max, which is the milliliters of oxygen that can be utilized per kilogram of body tissue. VO2 max is a pretty good estimate of an organism's capability of aerobic respiration, and so it lends itself beautifully to measuring race performances. And so that's why I use VDOTs. Just to better understand VDOT, here's a VDOT table. So let's say you run a mile in 8 minutes 1 second. That would give you a VDOT of 35. The equivalent 2 mile of that would be 1658, as you can see right here. And so you can see that there's a drop off. I mean, it's not a simple linear doubling of your 8 minute 1 second. It's doubling and change. After normalizing the data, I shaped the data by paring down the number of columns or attributes. Not all of them were important. For example, I didn't need to know the number of uploaded photos or the number of kudos or thumbs up that each run was given. So what I did was I took each marathon, each of my 13 marathons, and made a corresponding attribute. So I took all the training runs in the preceding 3 months and took, for example, the average distance per run, the aggregate distance, the total elevation climbed, the total numbers of runs, the average pace per run, etc. And so for every v dot for every marathon, so every marathon has a corresponding v dot, and for every v dot there's a string of attributes which are related to the for the 12 preceding weeks, or the 3 months preceding. This slide is a summary of my data set, and you can see the v dot information. You can see there's a minimum of 30.97 and a maximum of 60.95, which correspond to my slowest and fastest marathon respectively. Okay, so now that we have the data set normalized and shaped, let's get into the actual machine learning. So for this presentation, I use supervised learning and two forms of it: multiple linear regression and random forest. So for my regressions, I use multiple linear regression. We have multiple independent variables corresponding to one dependent variable. Our dependent variable in this case is v dot. So this slide, it's a test of the normality of my dependent data, which again is v dot, and you can see it's vaguely it has a vague Gaussian bell curve. There's a big gap right here, corresponding to the gap between my first and my second marathon. I didn't really train for the first one. Again, n equals 1. There's only one subject, so there's going to be some gaps in this data set. So this is the data frame that was resulting from the shaping and normalization of the data. You can see it's a it's a 12-row, 11-column table with the v dots on the left, and you can see 3 of the columns to the right of v dot that have the other attributes I was looking at. So these independent variables, or the attributes I'm looking at, are all listed right here. You have the average distance, which is the distance across all of the runs average, so per day, or per run rather. Then you have the average minute per mile, is the average pace. You have the total moving time, which is aggregated across the entire 3-month training cycle for that marathon, or that v dot. All right, so the results of the multiple linear regression, they didn't make sense. Here's an example why. Here's an example of what I'm talking about. So you can see here, average moving time, a 1% increase in average moving time corresponded to a 224.5% change in v dot. And also the total elevation delta. So the more feet climbed in the data set, the worse the v dot. So there's something going on here which I've missed in this study, or the data set is simply not big enough, right? This is a very low power study. A high power study, or a study, at least clinically, should have 200 subjects. This has one subject with 12 marathons. So it's just not enough points to make a good multiple linear regression model. So the second model I tried, it's another form of supervised learning, was random forest. In random forest, you bootstrap samples from the previously shaped and normalized data set, and then for each of these sample data sets that you made, you drive a decision tree for each one, and then you can view each decision tree as a vote, and then the decision tree that leads to the decision tree that has the most votes is the decision tree that the model selects um, as its predictor. The R package I used for this was R random forest. So to reiterate the project goals, number one, I wanted to make a model that could accurately predict a runner's time using the previous 3 months worth of Strava training data. And number two, I wanted to determine which attributes were most important in determining this marathon time. So with Random Forest, we bootstrapped 500 individual trees, and from that we derived the most important attributes in predicting a marathon VDOT or marathon time. Um, it seems to make sense as total distance, or the more you run, typically, the better you perform, and so that's reflected in these results. So it makes me feel better about the random forest model predictions versus the results from the multiple linear regression model. So next I wanted to test, can we accurately predict a marathon time based on 3 months preceding training logs. So I took the Delaware Marathon, which was in 2016, and this was extracted from my sample, my learning data, um, and then I put all the attributes inside my model, and I wanted to see what VDOT it spit out. And so you can see that the model spit out 57. It predicted a VDOT of 57 for the Delaware Marathon, as opposed to the actual VDOT, which is of 54. I'm not wholly satisfied by this because the VDOT is off by a good 10 minutes, so it's really not much better than throwing a shot in the dark, because it's about 30 seconds or 20 seconds per mile, which is a significant margin. It's a significant error. So what are the motivations for the project? Well, 3 of my hobbies are running, motorcycles, and video games. Number one, running. With the advent of Strava and using GPS data, there's a huge amount of running data out there that can be utilized for analysis. And I would like to figure out which factors in an athlete's training contribute to successful fast marathon times. And I've never seen it done using a informatics approach, and so that's my main motivation. Sometimes I even play video games on my motorcycle. But my most rewarding hobby has always been running, and I hope it always continues to inspire me to learn and to do more and more projects. Thank you. So in discussion, one of the issues was the number of subjects. Again, it's only n equals 1. There was one subject, and so a lot of linear models would not perform as well. Again, it was tested using a marathon from within that subject myself. So I don't know if that would be affected, but you cannot extrapolate it to general populations as reliably. Also, the number of marathons in the study, although there was a data set of more than 3,700 runs. Um, from those runs, there were only 11, 12 marathons that were utilized. Um, and so there was only really 11 or 12 data set entries. So this is a very low power and with a high beta error. So there's a big chance that um, you're going to erroneously claim that the null hypothesis is false. Thank you. This ends the conclusion. Oh, one more thing. Yeah, as a caveat, there were some unintended consequences of this GPS data being uploaded to Strava. And I thought it was interesting because it highlights some consequences of big data and public data becoming so ubiquitous and widespread and common and a lot. There's a lot of it. For example, some bicycle thieves would load up somebody's Strava and find out what bicycles they owned, their patterns when they would ride it, so to work or back home, and they would go and steal the bike when they knew the owner would be away, either working or sleeping. They would know exactly where to find what bike. Number two, um, there was a military base in Afghanistan, and getting some rest and recreation, some soldiers would go for a run, and unexpectedly they would trace large running routes in the desert, and in aggregate it would light up like a Christmas tree, almost revealing military base locations. Uh, so Strava became a threat to national security. I thought that was interesting. All right, thank you. Thanks for listening. Have a great day.